So right at the end there, I adjusted this this ramp and made it flat on the top, and I wanted to give a little bit sort of different scenario. So maybe what I'll do is I'll just copy this onto the next slide, and then I'm just gonna cut. No, that doesn't do it. I'll just erase this, and I'm going to move the box up onto the top. Okay, so suppose we have the box on the top there, and we're going to give it just a little bump so that it can ride down the ramp. Okay, so there's our ramp. That's that. So we're going to give it a little bump, and it's just going to ride down there. But on accident, we bump it the wrong way, and it falls down here. Okay, so it's going to fall some distance, and we can just kind of imagine. I don't want to imagine that it's tumbling or anything like that. We're not really ready for that kind of idea, but just imagine that we drop it, and it's going to fall under the force of gravity until it hits the ground. So it still has, force of gravity like that, but now our displacement looks like this. So delta x and force of gravity. And let's get rid of all of this stuff. And I want to do the same exact problem, but in this different scenario. Before I do that, I want to give you a little poll, and I want you to think about this for about a minute. I want you to think whether the final velocity we get in this scenario is going to be bigger or smaller or the same as the final velocity we got in the last. So we're going to have three options, and think it over. Just think, what's your instinct? Is it going to be going faster, slower, larger velocity, smaller velocity, or the same? Another minute to think about that. I really like everyone to respond, if possible, just what you think. And for one more response, whoever it is. All right, great. So what we have are 9 who say larger, 1 who says smaller, 1 who says the same. Okay, good. Now let's work it out and see what happens. I think we'll find this interesting. So we have network equals change in kinetic energy. Isn't this nice? It's already getting to be redundant sounding after just 3 problems because it's always the same. Now there's only one force here, so we just have work done by gravity. And that's equal to KE final minus KE initial. We know that KE initial is 0 because it's just being dropped. It's starting from rest. Work done from gravity we cannot cancel out because the angle between force of gravity and delta x is not 90 degrees. So instead of canceling it, we just write down the formula. Force of gravity, delta x, cosine of theta g, equals 1/2 mv final squared, where force of gravity is mg, and like before, the mass is going to cancel out. So the algebra is the same. We're going to multiply both sides by 2 and take the square root. So we get 2g delta x cosine of theta g. This is exactly what we got last time, but the delta x is different and the theta g is different. So let's start with theta g. Does anyone know what theta g should be? Come on, tell me, show off. Someone knows. Ziad?
Negative 90?
That's a good guess. It's not negative 90. Remember, what is theta g? What do we mean when we're picking an angle on the work formula? It's not the absolute angle, in which case you would be right. It's not the absolute angle on xy axes, but it's the angle between what and what. Stephanie?
Would it be 0 degrees?
It would be. How are you getting that?
Because you said it was like the angle next to the displacement and like they're both going in the exact same direction, so there's no angle.
Exactly. It's the angle between the force of gravity and the displacement, and they basically go exactly in the same direction. So that angle is 0. And the delta x, if we wanted to figure out what that is, if the length of the track was 2 meters, then this is going to be L times the sine of 30, which is just, 2 sine of 30, which happens to be 1 meter. So when we solve for v final, we're going to get square root of 2 times 9.8 times 1 meter times the cosine of 0, and this is 4.43 meters per second, which is the same. It's exactly the same speed if it just falls off of the back of the ramp versus slides down the length of the ramp. So that's really peculiar, right? Nobody really, or almost nobody, thought that's what would happen. In fact, I'm the one who picked this, so nobody else thought that this would happen. Why does it happen? And it's very curious, and I think kind of cool. So why do we get the same answer both ways? If we look at what we had before, we had square root of 2g, and then we just had L, which was the 2 meters, and then we had cosine of theta g, which was 60 degrees. Okay, that's what last time what we had. This delta x was just L, 2 meters, and then the cosine of theta g was cosine of 60. Well, this was the 60-degree angle up here, and L times the cosine of 60 would be the adjacent side here, which is exactly the height of this ramp. So we got the height of the ramp both times. There's a really good sort of philosophical reason for this. And I want to go back and look at the basic definition of work so we can understand it, because we'd like to be able to use this fact later on. So suppose we have a force vector like that, and a displacement vector like this. And what I said before for work was we would need to find the piece of the force that is in the same direction as displacement. So this is my force. This is my delta x. And there's an angle here. And what we got was the x component of the force times delta x, which would be F cosine of theta times delta x. But we could also think of this as F times delta x cosine of theta. Like from an algebra standpoint, these are identical, but from a philosophical standpoint, what is it? Well, we would be saying there's a piece of the displacement that is in the direction of the force. So this bit here would be delta x cosine of theta. And so we could think of the work as either that piece of the displacement that's in the direction of the force times the force, or the whole displacement times a piece of the force in the direction of the displacement. Now, I know it probably sounds like I'm speaking in tongues or something, but let's go back and look at this problem. So this object, it slides down the ramp. It turns out that when we're finding the work done by gravity, gravity only cares about how much of the displacement is in the vertical direction. That's this 1 meter. And no matter what the ramp looks like, when we do the math, that 1 meter comes out, whether it's 2 times cosine of 60 or 1 meter times cosine of 0, we get 1 meter. So the force of gravity only does work when the object moves, up or down, and it doesn't care about sideways motion. And for that reason, even if a ramp, just consider this for a minute, even if our ramp looked like this, and it was 1 meter tall and frictionless, as this thing slides down, when it gets to the bottom, the speed is going to be 4.43 meters per second. So this is a really kind of amazing fact of nature and a fact about how gravity works, that it only does work when we move in the vertical direction, and it does not matter at all about the sideways motion. In fact, this last picture I drew, this would be an impossible problem for us to solve using Newton's laws, because the acceleration would not be constant as it slides along here, so our kinematic equations don't work. But using energy, we can still solve it just as easily. So if we want to put that all together, then it turned out that we can just write down a work formula for gravity once and for all. And every time we see gravity as one of our forces, we can just use this formula. So the formula was just, if we look back here, in this case, it's easier to see because the cosine of theta g, or cosine of 0, is just 1. So what that was, the work was m times g times delta x, and the delta x was really just a height. So we can say m times g times delta y. That's how we find the work done by gravity. The only problem with this expression is that normally we're used to calling delta y. So here's my object, here's the force of gravity, here is delta y. Delta y would be a negative number in this picture, but the work done by gravity doesn't have a negative number in it because these are pointing in the same direction. So we kind of fix the formula by putting a little minus sign in there. So that way, if delta y is a negative number, that negative cancels off of the minus sign in front, and we get a positive amount of work. So we're going to practice doing other problems where we just use the formula for the work done by gravity. And this is the formula we will use no matter what the picture looks like. Okay, any questions about that? Ziad.
So you mentioned that for the two different problems that we've done, that we used 1 meter for both. Was that the point you were making with that?
Yeah, so my point was the first version we did, when we get to this stage, if we're plugging in numbers, the delta x times the cosine of theta g, which is right here, 2 times cosine of 60 equals 1 meter. And that's when it slides down the ramp, the 2 meter length times the cosine of 60 just gives us essentially the height here, which is 1 meter. And when we did it the other way, we had to develop that height was 1 meter by using some trigonometry on this triangle. But in both cases, the number that actually goes in to the formula for velocity for delta x cosine of theta g wound up being only 1 meter, which is precisely how far the thing falls, or delta y. So in fact, let's just do it one more time very quickly to see how we would use the work done by gravity. So if I have something here that's initial height is 1 meter and it falls down to the ground, so we would say delta y equals minus 1 meter. If the initial velocity is 0 and I want to find the final velocity, I would say net work equals change in kinetic energy. This would be work done by gravity, and that's KE final minus KE initial. But like before, there's no initial kinetic energy. Work done by gravity, we can now write just minus mg delta y. And here we have 1/2 mv final squared. So our masses cancel out, and v final squared will be minus 2g delta y, and we'd have square root of minus 2 times 9.8 times minus 1, and we get 4.43 meters per second. So the really relevant number is delta y. And again, this minus sign is only there to fix it, because when we usually use delta y, when something goes down, we give it a minus sign. And we don't want square root of a negative number, so we give it an extra minus sign to sort of fix the signs. Okay, other questions? All right, let's try a brand new problem. This is a problem we could have done and even did do using kinematics. Suppose, I think it was Robert Lewandowski who kicked a soccer ball off of a cliff. Let's say the ball is kicked with an initial speed of 35 meters per second, and the height of the cliff is 20 meters. This is going to go like this, and there's going to be some final velocity which we want to know. Now, we can solve this using kinematics. We wind up solving for time using the quadratic equation, and then we found Vfx and Vfy, and then use the Pythagorean theorem to say, you know, the Vf is the square root of Vx squared plus Vfy squared. That's just to remind you how we did before. But now we can do it using work and energy. We say net work equals change in kinetic energy. And while this thing is in the air, the only force is gravity. So the only work is gravity. We're going to have KE final minus KE initial. Now in this case, nothing cancels out. It has an initial velocity after it leaves Robert Lewandowski's foot. It has a final velocity the moment it hits the ground. So you should think initial, the moment after it leaves the foot, and final as the moment before it hits the ground. And gravity's doing work the whole way. So we're going to have minus mg times delta y equals 1/2 m v final squared minus 1/2 m v initial squared. The m's cancel. Multiply both sides by 2, get minus 2g. And delta y is going to be minus h. That's v final squared minus v initial squared. And so v final squared would be v initial squared plus 2 times g times h, because those two minus signs are going to cancel. And we get v final equals the square root of 35 squared plus 19.6 times 20. And I get 40.2 meters per second. Okay, now I want us to enjoy how easy this is. Because if we were doing this with kinematics, we would have to know the angle here, which I didn't even give you the angle. Why would we need to know the angle? Because we would have to split VI into x and y components because the kinematic mass equations have vectors. We would have to split this into components using sines and cosines. We don't even have the angle. So to do it without knowing the angle would actually be incredibly hard work, but it turns out it doesn't depend on the angle because we were able to solve it without the angle. So if you do all the work and you're really good with trigonometry, the angle winds up canceling out. And you would get VFY and VFX and then use the Pythagorean theorem. But we solved it in exactly the same way we solved the last three problems. Exactly the same. We start with the same equation. We do the same thing. Now that we know a formula for work done by gravity, it gets even easier. And there's the algebra here is very elementary. We cancel the m's, we multiply by 2, we move the initial squared to the other side, and then we take the square root. Those are all really, really easy algebra steps. And so we've just turned a problem that if I had offered them extra credit without giving you an angle, there's a good chance only 2 or 3 people would have been able to complete it. We turned it into just a very, very easy problem. So I really personally think you're all going to like this energy stuff a lot because you can do almost everything we were doing using kinematics and Newton's laws. You can do the same with energy, and it's easier. Raise your hand if it already seems easier to you. Good. That's awesome, because after you practice it, you haven't even practiced it yet. And yet, it probably is easier without having practiced it. Wait till you practice it, because when you practice it, this is something you really can just master. Okay? All right, any questions about this problem? All right, now let me talk for the remaining time. This issue with the work done by gravity, because gravity is such a kind of a special force, it's the work done by gravity really only depends upon where the object starts and where it stops. It just cares about delta y. We are going to make sort of a further improvement upon this, and it's going to make it even easier. And but it requires making a kind of a philosophical leap of sorts. So let me go back. I want to go back to the very beginning when we first started this very beginning, like an hour ago. Things move so fast in the summer class. So we started with this. The sum of the works equals the change in kinetic energy. And what we found is that the work done by gravity is kind of special because we have now a formula for it. So I'm going to split the sum of the work into the work done by gravity plus the work done by other forces. Okay? And I'm going to take the work done by gravity and I'm going to move it to the other side of the equation. Okay, so just bear with me. So I'm just calling this work OF, other forces. That's equal to delta KE minus the work done by gravity. Okay. So why am I doing this? I'm going to give you an analogy about energy that I think will be useful not only in this chapter, but going forward when we talk about thermal energy and other, in the second semester, for those of you who take second semester, when we talk about electrical energy. I think this sort of expanded discussion will be useful long term, this analogy. So think of energy like money, okay, like money in the bank account. And your total money in the bank account never changes unless somebody makes a deposit or a withdrawal from your account. So the left-hand side of the equation, these are deposits slash withdrawals. I can't say withdrawal without sounding like I have a drawl. Deposits and withdrawals. So if there's positive work, if the work is a positive number, then that's like a deposit to the account. It increases the energy of the system. If the work is a negative number, that's like making a withdrawal. So the kinetic energy, which represents the energy, the money in your account, it can go up or down, but only if there's a transaction. Okay? So what happens when I take the work done by gravity and I move it to the other side of the equation? The right-hand side is like money in the bank. Okay? So when I move the work done by gravity from the left-hand side to the right-hand side, this is like there's a deposit coming, but I am treating it like it's money in the bank already. I mean, we probably, most of us have experience with this. If you've got a stimulus check, there's a good chance you knew it was coming ahead of time. And in your mind, you were already thinking about that money as your money and how you were going to spend it. Okay, so in a sense, even though it was not really there yet, for you, it was very much money in the bank. You treated it that way. Raise your hand if anyone had that experience. Nobody got a stimulus check? Did anyone get a stimulus check? Nobody? Did students not get stimulus checks? Did you guys get screwed? Dustin? Did you get one?
I did, but it was very small.
Okay. Yeah, but okay, so I've got 4 kids, so I wound up with a big stimulus check. At any rate, you could think of it like an income tax refund if you've ever had one of those. The point being, there are times when the deposit hasn't been made. It might just be your paycheck, but you're already kind of planning and treating it like it's money in the bank because you trust that it's going to arrive. And the work done by gravity is that kind of thing. It's very reliable. We know that it works. I know that if I pick up, a bowling ball and I drop it, that gravity is going to do work on the bowling ball. It's going to give it kinetic energy. And if it lands on my foot, it's going to do work on my foot. So what we do by moving the work done by gravity to the other side is we're going to treat it like it's money in the bank already, which means we're treating it not like it's work, but like it is energy. So if we elaborate a little bit, the equation would be minus, because there's a minus sign because I changed sides, And then the formula for work done by gravity has another minus sign in it, minus mg times delta y. And so this becomes delta ke plus delta of the quantity mgy. So we're thinking of the work done by gravity, or technically this is minus the work done by gravity, as a delta of something. And this something, call it potential energy. Okay, potential energy. So what that means is, if I'm holding a bowling ball up in the air, I am so trusting that if I let go, it's going to smash my foot, that I treat the bowling ball as if it has the energy already. And it's perfectly fine to do that, because it's never been my experience that when I drop something like that, gravity doesn't do the work and give it the kinetic energy. Just like so far, I'm not sure about next year, but so far my income tax refunds have never bounced. But maybe the income tax refund will bounce next year. Maybe there will just be no money left in the government, and you'll be expecting a check and it never arrives. Maybe when we drop a bowling ball, the Earth disappears at that moment, and the bowling ball then has no reason to accelerate. Now, that's not going to happen, but maybe a better analogy is a bow and arrow. If I have a bow and arrow and I pull back the bowstring and I've got an arrow and I point it at someone, the person I'm pointing at, they are going to feel like the arrow already has lethal energy, because they know if I let go, the bow is going to give the arrow energy, and then it's gonna, it's gonna hurt them. Not that I would do that, but of course the bowstring could snap. The arrow may never get that lethal energy, but it's perfectly fine for us to imagine that it does. So what we're going to do going forward is we're going to, when we talk about work and energy, we're only going to count the work done by other forces, not gravity. Because gravity, we're going to take it into account by calling it potential energy. Now, this discussion I'm giving is probably geared more toward any of you who've had physics somewhere else. How many of you had a physics class sometime in your life, even physical science or something in middle school, where you heard about potential energy? Okay, most of you. So I guess I'm telling you this because potential energy is not real. There is no such thing. What there is gravity is going to do work, but we're going to pretend like it's real. And you know what? Honestly, it's a beautiful idea. And so in a sense, maybe forces are not real either. We don't see forces either. I just know that I believe in cause and effect. When I drop something and it accelerates, I believe that a force is necessary to cause that. And so we could think of energy in the same way. It's a beautiful idea. If there's one bit of physics that can stick with you beyond this class and that should stick with you, it's the idea of energy, potential energy, and the transformation of energy from kinetic energy to potential energy and back. Like if I just throw a ball or throw my pen up in the air, I'm giving it kinetic energy, and as it goes up in the air, it starts to lose kinetic energy, and as it loses kinetic energy, it gains potential energy. We're going to do some examples here, but I want you to kind of think about this as now on the right-hand side in our bank account, we now have two kinds of energy. And if there's no transactions, then the total energy doesn't change, but the energy can be transferred from one form to another. That's kind of like if you have a savings account and a checking account, and you can freely transfer money from one to the other within your accounts, but the balance has to stay constant unless you have a deposit or a withdrawal. Okay, so let's try a problem where we see how to use the potential energy concept. Okay, so I'm going to imagine that we have a ball and we kick the ball upward with an initial speed of 15 meters per second, and I want to find the maximum height. So we would start with network equals change in energy. But the change in energy now splits into change in kinetic energy plus change in potential energy. And the network, remember, we should be saying other forces. This is going to go up, this is going to come down. But we get sloppy, and I guess that's why I made this point, because your teachers in the past probably never told you that the potential energy was really just gravity doing work, and at some point in your life then, when you're solving a problem, you want to put the work done by gravity over here on the left, and potential energy on the right, and you cannot do that because you're counting the same thing twice. Okay, you can't do that. You cannot count the same thing twice. So you either can use the work done by gravity concept, but then you do not use the potential energy concept, or the preferred method is you do not use work done by gravity anymore. We just say there's no work, and instead we use the potential energy concept. So we're still starting in the same place, the work energy theorem. The network equals a change in energy, but now we have two kinds of energy, and as we go through a year of physics, we learn about more and more kinds of energy, but always it will be this way. The network equals a change in energy. Or we have to learn about other ways that we can transfer energy on the left-hand side. So here we have 0 on the left equals KE final minus KE initial plus PE final minus PE initial. And remember, my formula for PE is M times G times Y. And sometimes people write this as M times G times H, so you'll see both of those in the problem books. So if we imagine that Y equals 0 is where we start, then we could say this thing has no potential energy at the beginning. Additionally, we remember that max height means the velocity equals 0, at least for one-dimensional motion, if it's straight up and straight down. So we would say there's no final kinetic energy because it stops momentarily at the top. That's going to require you to kind of remember some stuff from chapter 2. And this means that the final potential energy equals the initial kinetic energy. So that would be mg times y final is equal to 1/2 m times v initial squared. The masses cancel, and y final would just be v initial squared over 2g. That's going to be 15 squared over 19.6. That's 11.48 meters. So that's how high it goes. Any questions? Okay, so that's probably it for examples for today, but I've been working very symbolically, and I've been cutting out plugging in numbers, which has allowed me to avoid even talking about the units of energy, but we should talk about them. If work is force times delta x times cosine of theta, and what work is it's a transfer of energy, then the units of energy would be newtons times meters. Cosine of theta has no units. And a newton times a meter is also known as a joule. So probably many of you have heard about joules, perhaps in a chemistry class or another physical science or physics class. But that's our basic unit. for many of our problems, we don't actually need to find a number, an amount of energy, but for some of them we do. So when you're solving problems, if you need as an intermediate step to report, what's the total kinetic energy or the total potential energy, then you're going to need to have, if you're doing work, it will be newtons times meters. If we're talking about kinetic energy, that's going to be, 1/2 mv squared, that's a kilogram, times meter per second squared, which gives you kilograms times meters per second squared times 1 more meter, and these guys are newtons. So the units of kinetic energy are the same as the units of work. They are newtons times meters. So you won't have to think a lot about units as long as you make sure your velocity is in meters per second and your mass is in kilograms. Your forces are in newtons, your displacements are in meters. The same goes for potential energy. We're going to have m times g, which is newtons, times the height, or the y, which is in meters. So as long as we stick with base metric units, meters, kilograms, meters per second, newtons, and so forth, we will automatically be getting the correct energy units, which are joules. Okay, any questions about the units? All right, so that's it for today. I will stop recording. Have a nice afternoon.